Hi guys, I'm recording this video because we missed the class in observance of election day. So first I will briefly leave what we learned in the previous class, and then I will cover what we will learn today, today's class. So in the previous class, we learned about abstraction. So you need to remember, so actually you need to know the concept or definition of abstraction. So what is abstraction? So difficult thing is hidden because this knowledge is not required for some operations or research or work. But we need to understand the only required things. So such as, I explained the abstraction with the analogy of a car, because in order to drive a car, we don't know about the very detail of the car inside of the car. So we don't know, we don't need to know how engine works, or we don't need to know the mechanism of brake systems in a car. So it's also true for the computer systems, because I explained that the computer system is very complex, and then also the computer systems are composed of many layers. So we need to only focus on the a few layers, one or two layers. So in this course, we will focus on this architecture layers, like architecture layer and the microarchitecture layer. Okay. So I also take an example of the abstraction of a process architecture with the Intel i7. So this is some abstraction level we will cover in this course. Okay. And also I will explain how the high-level codes are compiled and executed in the real processor. So we write code with the high-level language, high-level programming language like Python or C. Then I mentioned that these high-level languages are very similar to our natural languages, such as English. Okay, so but computers cannot understand these high-level programming languages, so these languages should be translated. And then compilers translate these high-level languages. And then if this code is compiled, then first the assembly code is generated. So if you see that this assembly code, actually the instructions in assembly code is represented in our natural characters like English. So as you can see, you can find some English characters here, SLLI, the X6, X11, and 3. So we see this assembly code, we briefly understand how code works. Actually, in this course, we will learn the assembly instructions of RISC-V ISA. But the computers cannot understand these English characters. So, right, the computer processor is a kind of digital system, and then digital systems can only understand digital signals, like electric signals, actually, like 1 and 0. So these assembly instructions to be represented in machine languages like this one. Okay. And so I briefly explain about the components in computer systems like this, this. Okay. Also, as you know, the computer processors are chips. That means the computer processor, the performance and cost of computer processors are tightly coupled with semiconductor technology. So that means if we apply the advanced semiconductor technologies in our processor chips, then we can achieve a higher performance and lower running costs, such as lower power consumption or lower energy consumption. So actually, the advances in semiconductor technology is tightly connected to the advance in computer processors. Okay. And then I briefly explain how the computer processors are implemented from the silicon wafers. So it's also somewhat common sense. So this is the figure of photo of the Intel i7 wafer dies. This is silicon wafers. So as you know, the silicon wafers are the shape of the shape of a silicon wafer is circle, and on a circle, the processor chips are fabricated. And then, you know, the shape of a chip is rectangle. So this single rectangle is called die. It's called die. It's not killed, but it's the name of this single chip is a die. Okay, so number of dies on a single wafer is determined by area of a single die. So as you know, so this is the 300 millimeter wafer, and then there are about 280 chips. And then what is the technology node? So technology node means the width of channel lengths in the CMOS transistors. And then if this technology node number is small, so that means that the size of transistor is also small. It's a small, okay? So if we use more advanced semiconductor technology, then we can build smaller chips if the number of transistors is the same, right? So in this figure, you can find the 280 chips, and then these dies are fabricated in 32 nanometer semiconductor technology. But this is the recent chips. The wafer size is the same, 300 millimeter wafers, and then there are about 500 chips. Why? The chip size is reduced, and then each chip is fabricated in 10 nanometer semiconductor technology. So if you just compare the channel width of this wafer and this wafer, so you can find that, the channel width is reduced. And then as I explained, if the channel width is reduced, then we can build a smaller transistor. And then if the size of the transistor is reduced, then we can include more transistors in the same area, right? So that's why we can get more chips from the same wafers. But as you know, the shape of a wafer is a circle, and shape of a die is a single die is a rectangle. So how about these chips, these dies? So we cannot fabricate the whole die in the boundary of a wafer. So we cannot use these dies. So we cannot use, okay? So I will explain about some approximate cost, the manufacturing cost of a computer processor. So first we can define the cost per die. So that is the manufacturing cost for building a single die, okay? So this is the cost per wafer divided by dies per wafer. It's the number of dies per wafer, and yield. So yield means it's a kind of successfully implemented die rate. So it's similar to the success rate. So what does that mean? So if you see these silicon wafers, so it's the actually the silicon wafer is the main material of the silicon wafer is silicon SiO2, or it's SiO2, silicon dioxide. So, but the material should be very pure. So if any defects are included in this silicon wafer, then we cannot use this defective die. Okay, so yield is defined by this equation, but you don't need to remember this equation because this is the empirical equation. It's just the empirical equation. So that's the defect per die multiplied by die areas. So this is the equation of the yield. So, and then, so what is the dies per wafer? The number of dies per wafer is approximately wafer area. It's the area of the this circular wafer and divided by die area. So it's an approximate equation because the shape is different, but usually we can use this equation. So what does that mean? Actually, the yield is determined by defect per area. So it is determined by semiconductor technology. We cannot control this technology because these semiconductor technologies are developed by fab. So that means that some semiconductor factory is called the fab, like FAB. And then, so there are two most popular fab company in the world. One of them is TSMC, and another one is Samsung. Okay. Also, the Intel has its own fab, but so recently Intel is struggling to develop the very advanced trend, actually the semiconductor technology. So, and you know, the Intel is now using 10 nanometer technology node, but recently the TSMC or Samsung are using 5 nanometer or 7 nanometer technology node. So we cannot control this defect per area, but you know, the yield is also determined by die area. Also dies per area, wafer is also determined by die area. So what does that mean? Cost per die is heavily influenced by die areas. Okay, if so die area means that the size of a single chip. If the size of a single chip is very large, then cost is also increased because so cost per die is inversely proportional to the dies per wafer. But as you know, the cost per die, so dies per wafer is the wafer area. It's the same. It's a constant, and then divided by die area. So it's actually is proportional to the die area. And then you know the yield is 1 plus defect per area multiplied by die area divided by 2, and then it's a square. So actually it's so then cost per die is also inversely proportional to the yield. So actually this is very similar to the die area square. So cost per die is actually proportional to the die area cube. Okay. So that means if we build very small chip, then we can reduce the manufacturing cost of the chip. So and then if the chip size is very large, then the manufacturing cost will be increased significantly because the cost per die is proportional to the cube of die area. And then die area is determined by architecture and circuit design. Okay, so architecture also decides the die area, also some circuit design methodology like our circuit design technology also decides the die area. Okay. Okay, so and then I will move on next topic. It's a performance. So in this topic, so we will learn about the how to measure performance of a computer processor. Okay. So and then I will take an analogy. So this graph shows some performance metric of the various airplanes, like so. And then if you see this graph, you can find that so passenger capacity of various airplanes. So this graph represents the speed. So no, it's a distance, the cruising range, and then so this graph represents the cruising speed, so speed of the airplanes, and then this is some it's a throughput. What does that mean? The throughput means that it's the number of passengers, it's a capacity multiplied by speed of an airplane. So as you can see, so we can find various performance metrics for airplanes. What does that mean? So if we just focus on the capacity, so number of passengers in a single airplane, so which airplane is the best? Oh, Airbus A380 is the best airplane if we just consider the number of passengers in a single airplane. How about the Boeing 737? So compared to the Airbus, then the capacity is about the quarter of the Airbus A380. How about the cruising range? Oh, this is so which airplane is the best? This one. How about the cruising speed? Oh, Concorde. Concorde is so actually it's very fast, but it's not manufactured today because it's very noisy, and then it consumes actually much gas. Okay, but if we just focused on the cruising speed, so speed of an airplane, which one is the best? Concorde. So how can you know? Actually, if the different performance metrics are considered, then the best airplane can be changed. Understand? So if we just focused on the passenger capacity, which is the best, Airbus, about the speed or Concorde, then how can you select the airplane for if you are a CEO? If you are a CEO of an airplane company, aviation company, then which airplane will you purchase? Okay. So firstly, you need to consider the performance. Why? Because if the airplane performance is good, then you will get more money, right? So, but then which airplane will you choose? It depends on the purpose of an airplane. What does that mean? So if we just focus on the number of passengers in a single flight, then you need choose airburst. But if you just focus on the speed, so from this city to the other city, and then if we just focus on the elapsed time between these two cities, then you will select the conclude. Right. What does that mean? So it means, so we can choose different performance metrics based on the purpose of our system, like our machine, right? So if we just focus on the capacity, then you can select the airburst. Then if you just focus on the speed, like let's say elapsed time, then we will select the conclude. Then how can we compare the performance of airplanes with some more reasonable performance metric? So we can calculate some metrics such as performance metrics such as throughput. So as you can see, what's the throughput? Throughput means the passengers, number of passengers multiplied by speed. So what does that mean? Which means some number of passengers with delivered within unit time, right? So throughput in this graph, throughput means the number of passengers per unit time, because we multiply the speed, then which is the best airburst. So if we calculate the new metric, new performance metric, then the best airplane can be different. So in this analogy, we can know that we can select the different performance metrics based on the purpose of a machine or purpose of a system. So if we just focus on the amount of workload, like the number of passengers per unit time, then we can also consider the throughput. But if we just focus on the elapsed time for a small amount of workload, like small number of passengers, but if we just focus on the elapsed time between the two cities, then we can just consider the speed. Okay, so it's also the same to the computer systems. So now I'll explain different metrics in the computer systems. Okay, but I made this slide for introduction. I just recording. So actually, in the computer systems, we use two representative performance metrics. The first one is response time, and then the second one is throughput. So it's a response time and then throughput. So actually, response time is similar to speed. So actually, so what does that mean? So response time is the elapsed time from start to end of a workload, right? So response time just measured how fast the machine works, right? So it measure how fast. But how about the throughput? What is the definition of a throughput? So definition of a throughput is the amount of total work done per unit time. So in the previous analogy, I also show the throughput of an airplane. So throughput means the amount of work performed within a unit time. So amount of work. So throughput represent how much per time, right? So we can use, so usually for the computer systems, we can measure the response time to measure the speed of our machine. Also, we can measure throughput, so that if we want to know how much work can be done during a unit time, then we can measure throughput. So you need to remember these two performance metrics. So actually this response time is frequently called latency. So latency is the elapsed time from start to end. And then throughput means so it's a definition is the amount of total work done per unit time. Okay. So please remember the definition of a response time or latency and the throughput. Okay. So actually, so from now on, so we will focus on response time, latency. So we will focus on the speed of a computer processor. Okay, that means that if the task is when the task is a certain task is executed in a computer processor, we can just measure the time at the start point, and then also we can measure the time at the end point, and then we can measure the elapsed time from end minus start time. So we just focus on this response time, so elapsed time, and then this elapsed time is called latency. Okay, so we will focus on this latency of a computer processor. So I will define the performance of a processor or a computer system. So the definition is important because it's just a definition. So you need to remember, so you need to memorize the exact meaning of a definition, right? It's just a definition. We cannot explain. So what is the definition of a performance? The definition of a performance is 1 over execution time. So that means the performance is inversely proportional to the execution time, like latency. 1 minus response, 1 over response time. So it's just the definition, okay? So why do we use this elapsed time for the definition of a performance? So we can say that, oh, if the response time is short, then we can say, oh, this processor is very fast. And then if the processor is fast, that means the performance is good, right? Performance, we can use high performance or low performance. So that means that the performance is high. And then if a processor is slow, so that means the application is run on a certain processor, but so the elapsed time is a little bit long. So that means we can say, oh, this processor is slow. So that means the performance of this processor is low. So we can say that performance is inversely proportional to the execution time. And then we can define the performance is the 1 over execution time. Okay, it's just a definition. Then why do we measure performance of computer systems? We need, if we want to compare the performance of two computer systems, then we can say that, oh, this computer system or computer system A is higher than the computer system B. So it's just a comparison. So why do we need to compare? Why do we need to compare the performance of two different computer systems? We just compare the performance of different systems, and then we want to buy, well, we want to choose better computer systems, so which have higher performance. So we can compare the performance. So like X, the computer system X is n times faster than computer system Y. So that means we just compare the performance of two computer systems X and Y. So how can you compare? The performance of system X is divided by the performance of system Y. And then, you know, the definition of performance is 1 over execution time. So we can say that. So this is equivalent to the execution time on computer system Y divided by execution time of computer system X. So we can say that, oh, X is n times faster than Y. It's n. So just to remember this representation. Actually, in a homework assignment or during in an exam, so you will be asked how to compare the performance of two different systems. Then you can conclude, you can answer like X is n times faster than Y, while the performance of X is n% higher than the performance of Y. Then you need to use this definition. Okay, so this is the example. So it's the same application. The same program is taken. It's run on the different computer systems A and B, and then it takes 10 seconds on A, and then it takes 15 seconds on B. How can we compare the performance of system A and B? So that is, so you are requested to compare the performance of systems A and B. So how can you compare? Each pop A divided by pop B. So it's equivalent to execution time of B divided by execution time A, right? Based on this definition. And so you are requested to compare the performance, then is the pop A divided by pop B. So it's easy. It's elementary question. It's elementary level question. It's the 1.5. So what does that mean? The system A is 1.5 times faster than system B. We can say that. Okay. And how can you measure the execution time of a certain application? So I mentioned a computer system, but we learned that a computer system is composed of many components like I/O systems, processor, memory, and storage, and network. So many components will influence the performance of a computer system, and that's true. But we want to compare the performance of different processors. And then also the difficult thing is that since a computer system is composed of many components, also the computer system is composed of many layers. So actually, when an application is executed, this normal user application is executed on a operating system environment, and then also this execution time is influenced by many components such as networks, I/O, interrupts, and then some other thread or applications. So thread by operating system, also some the management from operating systems. So it's very difficult to, so actually the elapsed time is the actual real performance in a computer system, but it's very hard. We cannot compare the performance of two processors fairly. We can, if we just measure the elapsed time of on a certain computer system, right? Because this elapsed time is influenced by many factors. So noise is very high. The noise is very much. So now to compare the performance of two different CPUs or two different processors, we just measure the CPU time. So the CPU time, just we assume that the program is just launched on a CPU, and then this program or this thread or application is not interrupted by operating system or other I/O devices or interrupts and then some other components. So we purely this single thread or single application is executed on a processor, and then we just measure the elapsed time of this application or thread. So this elapsed time or response time is called CPU time. Okay. So if we just compare the performance of two processors or two CPUs, then that means we just compare the CPU times. Okay. Okay. And then, the CPU is a kind of digital system, and then all digital systems are run with clock signals. So if you took the digital logic design course, then I believe you already know about the clock signals. So actually, this is the basic composition of this the system. So this is the combinational logic, and then these are sequential logic, like D flip-flops. And then the signals for this input, the input signals for this combinational logic are sampled by clock edge of this D flip-flop. And so the output of this combinational logic is sampled by the next rising edge of clock signal in this D flip-flop. So the processing time of this combinational logic should be within a clock period of this logic, like this digital system. So we can because the CPUs require clock signals for operation, then this frequency, that means the clock period or some clock frequency is clock frequency or clock clock period influence the CPU time. That's the response time of an application. So we can just see the processor like this. So this is the instruction, and then this is a processor, and this is another flip-flop. So if the instruction is given to a processor, then the instruction is executed. And after some clocks, the output of this instruction is generated. So as the systems or the CPUs are working with clock signals, you can count the clock cycles. Also, we can also measure the clock period time. Then we can easily measure the CPU time. Okay, so I explain here. So what is the CPU time? So CPU time, what is the definition of the CPU time? It's the execution time of an application in a processor. Okay, and then this execution is not interrupted by other components or interrupts. Okay, then how can you measure this execution time? So we know this CPU is working with clock signals. Okay, then we can count number of clock cycles during the execution of this application. Okay, we can count the clock cycles. So that means the number of clocks. So number of consumed clocks from start of an application and then to the end of an application. You can count the clock cycles. And then if this number of clock cycles are multiplied by clock period, so clock cycle time, then we can just calculate the CPU time. Why? You know, the clock signal is the repeated signal. So clock period is the constant. The clock period of a single clock cycle is the same for every clock cycle. So you can easily calculate the CPU time as the clock cycles, number of clock cycles multiplied by clock period. And then clock period is the 1 over clock rate or frequency. Okay, so actually CPU time is the number of CPU clock cycles divided by clock rate. Right. It's very easy. It's obvious actually. Right. So then how can you increase the performance? So CPU time is the number of clock cycles divided by clock rate. So how can we increase the performance? So in order to increase the performance of a CPU, then we need to reduce CPU time. Right. How can you reduce CPU time? So by this equation. So if we just understand the equation, then we can find a solution to on some issues or problems, right? So how can we reduce clock cycle CPU time? So if we reduce the number of clock cycles, then we can reduce CPU time, obviously. And then another factor is clock rate. If we increase the clock rate or clock frequency, then we can reduce CPU time because CPU time is inversely proportional to clock rate. And so this is performance can be improved by reducing number of clock cycles and increasing clock rate. It's obvious and it's very simple. I believe it's easy. I believe it's easy to understand. Then why did I mention these two components? Then how can we reduce number of clock cycles? It is determined by software and architecture. How about the clock rate? Clock rate is determined by clock speed. And then, the clock frequency. Then clock frequency is determined by hardware design. And so which means the clock rate or clock frequency is determined by the design effort or some design techniques, like the implementation, the hardware implementation of a CPU. So clock rate is usually determined by hardware. So also in the number of clock cycles, I mentioned that this factor is determined by software and architecture, but usually software. So not to increase the performance of a computer system, then we can focus on the software part and hardware part. So hardware designer will focus on this hardware part, the clock rate. Clock rate is determined by architecture, like microarchitecture and hardware design and hardware implementation. Also, this clock rate is determined by semiconductor technology. How about the number of clock cycles? It is determined by architecture and software, so application. Okay, also instruction set architecture. So we can divide some factors with the software part and hardware part like this. Okay, this is an example. So computer A works with 2 gigahertz clock, and then CPU time is 10 seconds. Then we can easily compute the number of cycles for this computer A. And then you are requested to design new computer B, and then you are requested to reduce the CPU time as 6 seconds. So performance is improved by 10/6. So in order to increase the performance of this computer B, then we can use fast clock. But if we use this fast clock, then number of clock cycles can be increased. Okay. So in the previous slide, I explained that this is the software part and that this is the hardware part, but it's not clearly divided. So actually, these factors are also influenced by software and hardware. So it's also true because actually the architectures are both architecture techniques influence the number of clock cycles and clock rate both. Okay. So if we use the faster clock, then the clock cycles can be increased. This is the 1.2 2. Then how can we decide the clock rate of computer B? So the clock rate of B is, so by equation is like this, and then the clock cycle of B, and then divided by CPU time of B. The CPU time is given here, so it's a 6 seconds. And then what is the clock cycles of computer B? It's 1.2 multiplied by clock cycle A. And what is the clock cycle A? The clock cycle A is the CPU time A multiplied by clock rate. So it's 10 seconds and then 2 gigahertz. 2 gigahertz is a 10 to 2 multiplied by 10 to 9. So it's this 20 multiplied by 10 to 9. Then what is the clock rate of B? So we already compute the clock cycles of A, 10, like this. So 4 gigahertz. Okay, it's very easy, right? So actually, if we know the this equation, actually, but this equation is very obvious. So we just count the number of clock cycles, and then this number of clock cycles are multiplied by clock period, clock cycle time. And then actually the clock cycle time is equivalent to 1 over clock rate. Because the equation is very easy, then we can solve this equation very easily, right? So what is the required clock rate? It's 4 gigahertz. Oh, it's twice of computer A. Okay. So now, I will also explain the performance by instruction count and CPI. So in the previous slide, what is the CPU time? CPU time is the CPU number of clock cycles multiplied by clock cycle time. And then I explained that usually this factor is determined by hardware effort, like hardware design or microarchitecture. Then how can we define this part? You know, what is the computer? This is a computer or a processor actually. Okay, let's see, this is processor. Processor hardware. Then what is a processor? Processor, a computer processor receives instructions. So what is an instruction? It's like add, sub, load, right? So any instructions such as like arithmetic instructions such as add, sub, subtraction, and multiply or divide. Also, the computer processor requires the some data transfer instructions like load and store. So these are kind of instructions. So what is a processor? If an instruction is given to a processor and this processor generate a result defined by this instruction. So what does that mean? Computer processor execute multiple instructions one by one. And then these multiple instructions means it's a group of instructions. Group of instructions is just an application, right? A program. What's the program? It's group of instructions. Then how can we calculate the clock cycles with instruction count. So, the instructions are given to a processor, then we can count the number of instructions given to a processor. And then this number of instructions, I said the program is a group of instructions. So if a program is given, then we can count the number of instructions in this program, right? So we can count the number of instructions is called instruction count. And then how can we calculate the clock cycles? If we know the number of cycles per instruction, so average number of cycles per instruction. So that means that it's the taken cycles when an instruction is executed by a processor. So what does that mean? If a instruction is given to a processor and then it consumes 2 cycles, then what is the cycle per this instruction? It's 2. And then B instruction is given to this processor, the same processor, but it takes 1 cycle. So what is the CPI for this instruction? The clock cycles per instruction, it's 1. So cycles per instruction is just a taken number of cycles when executing an instruction. Okay, then easy. So what is the clock cycles? Clock cycles are equivalent to instruction count, number of instructions, and then multiplied by cycles per instruction. Wait, what is the cycle per cycle? Actually, this is it's an IC, the instruction count, and then what is the cycles per instruction? It's cycles per instruction. So it's a clock cycles. It's obvious, right? But why do we divide the clock cycles like this? It's related to the software part, also architecture part. So based on this part, we can also analyze the performance of our computer system, and then we can focus on some different areas like software, architecture, or some hardware part. Okay. Then how can we calculate the CPU time? It's easy also. So we can just replace the clock cycles with the instruction count multiplied by cycles per instruction, right? So CPU time is the instruction count multiplied by cycles per instruction. This is called CPI, and multiplied by clock cycle time. So this is the clock cycles. So we can rewrite this equation like instruction count multiplied by CPI and clock rate. So this is the equation for performance on a certain CPU processor. So we can rewrite CPU time. CPU time is instruction count. So I frequently use the IC multiplied by CPI multiplied by T. T means the clock cycle time. That's the clock period. So just remember this equation. We frequently use this equation to calculate the CPU time. Okay. So then this CPU time has 3 factors: instruction count, CPI, and clock period or clock cycle time. I already explained about the clock cycle time. Then how CPI is determined and how instruction count is determined. The instruction count is determined by actually program. If the program size is very large, which means the instruction count is also large. But if the program size is small, small, so which means the instruction count is also small. So usually the instruction count is determined by program. But I explained that high-level language, so program written in high-level languages is compiled to the assembly code. Then this assembly code is compiled to machine languages. So we need a compiler. Then how this high-level languages, the high-level language code is translated. So actually, the computer processor receives the machine code, and then actually each line of the machine code is one-to-one mapped to the each line of assembly code. So actually, the number of instructions given to a processor is usually. So sometimes we can use some different syntax in assembly code, but usually the number of instructions in a program is equivalent to the number of lines of assembly code. Okay, so the high-level language code is translated to the assembly code based on the instruction set architecture. So it's like this. This is a program written in C. It's a C program. And then this same C program can be compiled using x86 ISA because, and then binary code will be generated. And then the same C program can be compiled with ARM ISA. And then because the instructions in x86 and ARM ISAs are different, the number of instructions after compilation can be also different. Understand? Because instruction set architecture is different, and then after compilation is a compiled process, the final number of instructions can be different if different ISAs are applied. So instruction count is also determined by ISA instruction set architecture like x86 or ARM. Also, instruction counts are determined by compiler optimization. Okay, so it's a compiler techniques. But usually this part, so ISA is just the architecture, but program and compiler is software, right? Okay, so it's a software part. So instruction count for a program is usually determined by software. And then how about the average cycles per instruction? It's determined by hardware, actually, micro architecture. So what does that mean? So same program can be executed by Intel CPU and AMD CPU. But you know, the Intel CPU and the AMD CPU is a different hardware, but these CPUs can execute the same x86 application, right? But because the hardware is different, so the CPI, the required clock cycles per instructions can be also different. So the CPI is high, so that means that for executing a single instruction, then more clocks are taken. So which means that the performance can be low because the overall performance is determined by also CPI and clock rate. But even though the binary code, so that means the application, the number of instruction count is the same, the CPI can be different. So DPI is determined by CPU hardware. Then usually the CPI is determined by microarchitecture, the architecture of a processor. So different processor may have different CPI value. So instruction count is a software part. So CPI is also hardware part, but usually microarchitecture is architecture part. The T, the clock cycle is the design part, hardware design part. So for the software part, we can focus on the instruction count of a compiled software. And for CPI also decides the CPU time. So we can focus on the microarchitecture of a processor. Now about design, hardware implementation, we can focus on the clock cycle time. So this is the example. So for computer A, the cycle time is 250 picosecond, and then CPI is 2.0. And then computer B, the cycle time is 500 picosecond, CPI is 1.2. The same ISR, then same compiler option, then same software, same application. So the same compiler option, and then same application is executed on different computers. And which is faster and how much? So you mean that you are requested to compare the performance of two different computer systems. So how can you compare the performance? Each perf A divided by perf B, which is execution time. So but we just measure the CPU time. So CPU time is the execution time. CPU time B divided by CPU time A, right? Then if we just calculate the CPU time B and the CPU time A, then we can compare the performance, right? How can we calculate the CPU time A? That is the instruction count multiplied by CPI of A and the cycle time of A. So that is it's the instruction count is the same because in this example, we assume that it's computer A and computer B use the same ISA, instructions and architecture, and then same compiler option, and then same application, right? So this is the CPI is 2, and then time 250, so it's I multiplied by 500. How about the CPU time B? I multiplied by 600. So we can just replace the here and here. It's 1.2. It's very easy. So how can we say processor A is 1.2 times faster than processor B, right? So okay, I believe everyone can understand because this is not difficult. And then, so also for the different instruction classes, the CPIs can be also different. So instruction classes means that some instructions are arithmetic instructions or logic instructions. Just you know, that is in the as add, plus, minus, multiply, divide, and the logic instructions like and or exclude or some logic operation. And then there are some other classes, instruction classes such as the data transfers like load and store. And then another class of an instruction is the branch instruction. It's control instructions. So usually we classify the processor instructions as arithmetic logic instructions and data transfer instructions and control instructions. Okay, but in a processor, different instruction classes may have different number of cycles. Okay, because the number of cycles in a processor is determined by architecture, like microarchitecture. And then different kind of instructions can have different clock cycles. So and then if the different instruction classes have the different CPI values, then we can calculate the clock cycles like the CPI of some instruction class I multiplied by instruction count of class I. And then we integrate for all kinds of instruction classes. Okay. Also, based on this instruction, the rate ratios of instruction count of a certain instruction class, then we can calculate the weighted average CPI. So it's weighted average. The CPI is the total clock cycles divided by total instruction count. So we can rewrite this equation like CPI I divided by ratios of a certain instruction class. So this is the CPIs of instruction class I multiplied by ratio of instruction class I out of total instruction count. So this is the weighted average CPI. So you can, I believe you can understand with this example. So this is the instruction class A and class B and class C. So instruction class in sequence, the CPI for this, the CPIs for each class is shown like 1, 2, 3. So it's a CPI for class A is 1. CPI for class B instruction is 2. CPI for class C instruction is 3. And this row represents the instruction count in sequence 1. So some application F1. So it's 2, is instruction count is 2, and then instruction count is 1 and 2. And then this is the different applications F2. The instruction count in sequence 2 is the class A is 4, 1, 1. And then you are requested to calculate the average CPI for different sequences. Okay. So in the sequence 1, what is the total instruction count? It's 2 plus 1 plus 2 is 5. So 5. And then what is the total clock cycles? What is the number of total cycles? So in sequence 1, the class A, there are 2 class A instructions. So 2, what is the CPI? Is 1. So 2, so what is the total cycles of class A instructions? It's 2 multiplied by 1. This is same to the class B, 1 multiplied by 2, C, 2 multiplied by 3. So total cycles, number of total cycles is 10. And then by definition, average CPI is the total cycles divided by total instruction count is 2. How about the sequence 2? With the same way, the clock cycle total number of clock cycles is 9. And then total instruction count is 6. Right. So average CPI is 9 divided by 6 is 1.5. So we can calculate CPI based on definition of a CPI. What's that? Number of total clock cycles divided by number of total instruction count. And then different instruction classes can have different CPIs, like this. So, and then if we know the instruction count of the different instruction classes, then we can easily calculate the total cycles based on this information, right? Like this. Then we calculate the average CPI. So if you remember the definition of a CPI, then based on this provided information, you can easily calculate the CPI. But okay, well, you know, if the application is different, then the ratios, like frequencies of different instruction classes, can be different also. Then CPI can be also different. Okay. So it's a summary. So please remember this equation, the CPU time. The CPU time is the instruction count, so it's the, which means is number of total instructions in a program, multiplied by CPI is the clock cycles divided by total instructions, multiplied by T, clock cycle time. Then, you know, these factors are determined by some different layers was different software, hardware, microarchitecture, or architecture. So for example, algorithm of an instruction influences instruction count or CPI because the instruction frequencies can be different. And then programming languages such as C and Python influences instruction count and CPI, compiler and CPI. So these are actually the software part. Instruction architecture, ISA, like x86 or ARM, influences IC, CPI, and TC. Okay. Okay. So I will stop here. So actually, this equation is very important for this topic. So please remember and understand this equation. Okay. So I stop here, and I hope everyone watches this recorded video before the next class. Then, okay, I'll see you in the class on the coming Monday. Okay, bye guys.